In the previous video, we mentioned how what we're really doing is taking this area under a curve that we're interested in and trying to subdivide it up into intervals in which we put a basic shape sort of in that interval to approximate the area in that interval. Now that's very, very wordy. What we're really doing is placing a bunch of shapes underneath that curve and computing the area of each of those shapes individually and then adding them together. And the first one we're going to do exactly is the first one we're going to practice is using trapezoids. So remember, Riemann sums from Calc A were associated with rectangles. We're going to be placing some trapezoids under a curve here. So let's just consider this very general function. F of x could be anything we really want, and we're going to compute the integral of f of x between 0 and 1. So we have x equals 0 here, and we have, let's just say, x equals 1 somewhere here. So we're really interested in trying to compute this area all underneath the curve that I just shaded in. So this is the problem at hand. What is that area under that curve? And remember, we're thinking of f of x in general as a function that we can't exactly integrate, which is why we're going towards integral approximations. So let's make this problem a little more explicit. So for us in this example, we're going to try to approximate the area under the curve with 4 rectangles. So I'm telling you right off the bat how many trapezoids, we're going to be using in this case. So what that means is we will need to subdivide our interval between 0 and 1 into 4 different regions, or what we call partitions. So if we do that in this case, well, we know if we just divide this into 4 regions equally between 0 and 1, this will be 1/4, 1/2, and 3/4. So really what we're then asking is, okay, we have these points along the curve that we're then going to use. And if this was in Calc A, we would be trying to put rectangles between these points using left-hand rule or right-hand rule in that idea. For us right now, we're going to practice putting trapezoids. So remember, for us, if you haven't thought about trapezoids in a while, these are 4-sided polygons where it has one set of parallel lines. And for us, those parallel lines are going to be those vertical kind of dotted lines I have. So for example, if we just draw a trapezoid within the first interval, the trapezoid, we then connect the red dots along the curve. And what we outlined in purple defines our trapezoid. Now, mind you, we know the value of the function at those dots because we're given the function itself inside of this integral. So we have almost all the information we need to actually compute, say, what is the area of that trapezoid in that first kind of partition. So remember, for us, the other thing that's useful is the area of a trapezoid is equal to 1/2 times what we'll say height 1 plus height 2 times the base. Now for us in this example, the heights are going to be our function values. And the base is going to be the partition width, which is actually just going to be the space between those vertical parallel lines that outline our trapezoids. So we see that each of these trapezoids will have a different h1 and h2, depending on which function values we're grabbing, depending on the x values on the left and right sides. So again, B is the width of the partition. So when we think of, say, the area of trapezoid 1, the area of trapezoid 1 will be, well, using the formula, it's going to be 1/2 times h1, which is the function value of the left side. So that'll be the value here, which in this case is our function evaluated at 0. Whereas the second point for h2 will be our function evaluated at x equals 1/4. And the last thing we need is, well, what is the width of the interval? And the width of these intervals, because we subdivided 0 to 1 into 4 equally spaced partitions, the width of the interval is just going to be 1/4. So again, that was our B from our formula. And these are both our h1 and h2 values. Let's make this a little more clear. F of x0 or f of 0 is h1, and f of 1/4 is h2. And we're going to do this for each of those trapezoids. So just to make this a little more explicit, when we have our integration or our definite integral between 0 and 1 of f of x, we're really saying that this definite integral is approximately equal to the area of these 4 trapezoids being added together. So we're really just taking the area of 4 trapezoids, adding them together and saying that that might be an approximation of the area under that curve for us. So let's go ahead and just do this. So we figured out what the area was for the first trapezoid. That was what is given above, 1/2 f of 0 plus f of 1/4 times 1/4. So that was our area for trapezoid 1. If we look at the area for trapezoid 2, well, it's going to have a familiar flavor. We're just going to take the function values from the left and the right side. So again, the left side being the function value at 1/4, and the right side being the function value at 1/2. And that's going to outline for us our trapezoid that will compute the area for A2. And we're going to do the same exact process for A3 and A4, just using the left and right function values for each of those separate partitions. So if we keep doing that, we'll just use our area formula for the second trapezoid. So 1/2 times the function value on the left side, which is 1/4, plus the function value on the right side, which happens to be 1/2. Times the width of that interval, which is still 1/4 since they're equally spaced. Again, the 1/4 is coming from us subdividing the region 0 to 1 into 4 equally spaced pieces. So that is our area for trapezoid 2, and we would do the same exact thing for trapezoids 3 and 4. So if you just bear with me a second, filling in all of these details. So if we're looking at the area for trapezoid 3, we would need 1/2 as the x value on the left and 3/4 as the x value on the right for the trapezoid in the third spot. And then for this last trapezoid, we're going to need, well, the value on the left, which is 3/4, and then the furthest most value on the right, which is x equals 1. And that'll define the fourth area for us for that trapezoid. And if we just end up doing all of those function evaluations at 0, 1/4, 1/2, 3/4, and 1, plugging them into that formula that we have there, and adding all four of these areas together, we have an approximation of the area under that curve using trapezoid rule. Now, if you notice, there's a couple things that each of these terms have in common. So if we just take note of this, each term of this sum has a 1/2 sitting out in front. Each of these terms also has this 1/4 kind of at the very end. So we're just going to pull that 1/2 and 1/4 out in front. So I'll divide by 2, and I'm just going to put this 1/2, or sorry, this 1/4 up in the numerator. And if we write out this entire thing as a big old sum, we would see, well, it looks like there's only one x f of x0. Now, if we take a look at the next one, we're going to see that there's actually, well, there's a couple evaluations of functions at 1/4. So we get actually 2 times f of 1/4. We're also going to see on that same note, there's 2 different function evaluations at 1/2. We have the one from area of trapezoid 2, and we have the one from area of trapezoid 3. So we're going to add 2 of those together. And in a similar vein, we have 2 different function evaluations of f of 3/4 and f of 3/4 coming from the third and the fourth trapezoids. But then we're going to see that there's only one f of 1 evaluation at the rightmost endpoint of our integration interval. So we only have +1 f of 1. And the reason I wanted to go through this very last kind of step is our book is going to introduce this as a general type of formula for trapezoid rule, where we have basically the width of our intervals out in front, always divided by 2. And then we have the endpoints evaluated at 1 time each, but then these middle points, we multiply each of their values by 2 when adding them together. So we'll see this formula kind of come up in class, but this is the big idea for trapezoid rule, computing the areas of individual trapezoids and then adding them all together. And of course, in this example, we didn't specify what that function f of x actually is. This function f of x could have been really, really complex and intricate, but all we're doing to approximate its value or its definite integral is computing its value at a few different values of x.